We finished chapter 4, and now we know enough techniques, the product rule, the chain rule, the quotient rule, and we know to find derivatives of simple functions like x to the n, exponential and logarithmic functions. Combining all this together, we can now differentiate anything anyone ever gives to us. Just about. So now we're moving on. We want to do stuff with these derivatives. We won't get to our main applications just yet. We've still got a bit of theory to go through. But chapter 5, which we're starting today, 5.1, is increasing and decreasing functions. And I suspect if I gave you a function right now and just said, is this function increasing or decreasing, you could look at the graph and tell me the answer, right? For example, here's a function. Here's y equals f of x. If I asked you, is this function increasing or decreasing, well, you'd look at this and you'd say, okay, as I move from left to right, we always read graphs as moving from left to right. Imagine this is like a roller coaster, and you're moving along it. As you go from left to right, your y values are getting bigger and bigger and bigger, right? You're going up in value. So this is clearly an increasing function. But what I want to do is I want to give you just a very mathematically rigorous definition of this. Being able to look at a function and identify increasing and having this intuitive idea in your head is sufficient, I suppose. But let me give you the mathematically rigorous definition. Here it is. A function is increasing. A function is increasing on an interval. So we always talk about increasing on particular intervals. Here, it's actually increasing everywhere, from minus infinity to positive infinity. But a function is increasing on an interval if f of x1 is less than f of x2 whenever x1 is less than x2. Right? And what are x1 and x2? Well, they're just any old two numbers from the interval. Right? So for any x1, x2 in the interval. So what does that mean? We'll come back over here, right? I claimed that this was increasing everywhere, so I should be able to choose any two numbers. Choose any two numbers where x1 is less than x2, right? So here's x1. I choose this guy to be x1. Now x2 has to be chosen to be bigger, so choose any x2. How about this one? Increasing means that no matter how I choose these, my y values here, that y value is f of x1, and this y value up here, f of x2, I should always have that this y value corresponding to the bigger x value is bigger than the y value corresponding to the smaller x value. And that is true. Convince yourself of this. Convince yourself no matter how I choose x1 and x2, my y values are always getting bigger, right? As I move from left to right, the y values are increasing, so that's what it means to be an increasing function. And similarly, decreasing on an interval. What do you think that would mean? Well, let's draw a decreasing function. So here's a function that's always decreasing, right? Y equals f of x. Why is it decreasing? Well, because as I move from left to right, again, think of this as a roller coaster. If I move from left to right, as I go towards the right, my y values are getting smaller and smaller and smaller, right? It's decreasing in value. So if I want to go with a similar definition, what should this mean? Well, let's go with the same idea of, okay, I choose an x1, and then I choose an x2 that's bigger. Well, to be decreasing, that should mean that my y values are getting smaller, right? The smaller x value should actually correspond to a bigger y value. So our definition here is going to be similarly decreasing on an interval if f of x1 is actually bigger than f of x2 whenever x1 is less than x2. Right? If you choose a point to the left and then a point to the right on the right, The bigger point has a smaller y value, is what this definition is. So this is a decreasing function. Okay, but again, your intuition is enough, right? As long as you understand that as I move from left to right, if my y values get smaller, I'm decreasing. If they get bigger, I'm increasing. That's fine. Here's our function. I'm going to label a couple of interesting points. This point right here that matches the bottom of that valley. Let's say, I don't know, let's call that -2. Alright, now this y value over here that matches the top of this hill, it looks just a little bit further away from the origin. Let's call that +3. And then the point right here that matches the bottom of that ravine or whatever, let's say that's 5. It looks more like a 6 to me. We'll go 6. Doesn't really matter. Right, my question is, where is this function increasing and where is it decreasing? Well, if I start over here at -infinity, right, -infinity is way out this way, and this is +infinity way out here. As I come from -infinity, this graph suggests that it just continues on like this forever, right? If you stop drawing the rest of it, it's supposed to mean it just continues like this forever. As I come from -infinity, I'm always decreasing, right? I'm decreasing, 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 decreasing until I get to x equals -2. And then I start to increase after that, right? So where is it decreasing? Well, it's decreasing from -infinity to -2. And depending on the textbook that you use, some people will say, yeah, it's actually still decreasing right here at the very bottom. But in my mind, it's actually neither decreasing nor increasing, not according to our definition. Right, so that's why I have a round bracket here. At -2, it's actually neither. It's flat, instantaneously flat right here. So we're going to exclude it. We're just going to do a round bracket there. So from -infinity to -2, not including -2, we're decreasing. And then it starts to increase again, right? Then it starts to increase. So from -2, it increases, 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 all the way until the top of this hill right here, which happens to x equals 3. So it's increasing from -2 to +3. Again, I'm not going to include +3 because it's neither increasing nor decreasing there. It's just flat. And then it starts to decrease again. Right? It starts to decrease again. So you could use words here. You could say it's decreasing on this interval and another interval, but I'm going to use the mathematical symbol. We'll go with a union of intervals. So it just means and. The way you should read that in your mind is and. So from -infinity to -2, and from 3 to 6 it decreases, right? So from 3 to 6. And then last but not least, it passes 6. At 6, it's neither increasing nor decreasing. It's the derivative isn't even defined there because it's got this sharp corner. But then it starts to increase forevermore. Right? So it's increasing on -2 to 3 and, so I'll use the union symbol, and 6 to infinity. Okay? So this is a skill you should have. You should be able to look at the graph of a function and identify where is it increasing, where is it decreasing, and tell somebody the intervals on which it increases and decreases. But we want to do more than this, right? You don't often just have a graph of a function on hand all the time, right? You usually have an algebraic expression. Here's my function, f of x equals x squared plus 2, right? So without looking at the graph, the question is, where is it increasing and decreasing? And we want to be able to answer that question. We want to algebraically answer that without having to graph the function. Alright, so the answer to that question actually comes from the derivative, right? Because derivatives tell us what? They tell us about slopes. They tell us about slopes. So what does that mean, right? If a function has a positive derivative, that should mean that it's got a positive slope. It's sloping upwards. The rate of change is positive. It's an I'm giving it away right now, but if you have a positive slope, then you must be an increasing function, right? If your values are increasing, because you have a positive slope, then that's what it means to be an increasing function. So here's the observations. If the derivative is positive, if f prime of x is bigger than 0, for each x in an interval, then f of x is increasing. So it looks like that, right? More or less. It could curve either direction, but it would be an increasing function, so it's going up. It's increasing on that interval. So now you can answer this question algebraically. If I say, where is a function increasing, you would take its derivative and ask yourself, where is my derivative positive? Similarly, negative derivative would mean downward slope, so decreasing y value, so it would be a decreasing function. If f prime of x is bigger than 0, or decreasing, is less than 0 for each x in an interval, should have an n there, then f of x is decreasing. Decreasing on that interval. Okay, so if I asked you where's a function decreasing, you take its derivative, and you ask where's my derivative negative? When is it less than 0? This doesn't exhaust all the possibilities though, right? Bigger than 0, less than 0, it's possible your derivative is equal to 0, right? That's our third possible case. But what do you think that means? Well, if derivative equals 0, then it's got 0 slope, right? It looks like a horizontal line. It's neither increasing nor decreasing. And what types of functions give you 0 derivative? Constant functions, right? So if f prime of x is equal to 0 for each x in an interval, then f of x is neither increasing nor decreasing. F of x is constant on that interval. And we're going to make one more observation. I'm going to redraw that graph I had. I'm going to point out something important about it. So my graph looked something like this. Close enough reproduction, I think. And you'll notice that these points that I have labeled, -2, 3, and 6, they're important. Why are they important? Because they're the points where it changes, right? It goes from decreasing to increasing. So at -2 it changes from decreasing to increasing. At 3 it changes from increasing to decreasing. And then at 6 it changes from decreasing back to increasing. Right? So notice that at the points where f of x changes from increasing to decreasing, these are -2, 3, and 6. Those are actual just English parentheses now, right? I'm not indicating any math happening here. I'm just putting the values in parentheses. -2, 3, and 6. What happens at -2? What's my derivative? Well, if you put a tangent line down here, it'd be totally flat, right? So at -2, my derivative is 0. What about at 3? Same thing. put a tangent line down there, my slope is 0, so my derivative at 3 would be 0. And at 6, what's my slope? Well, at 6 it's the sharp corner, so the derivative isn't defined, right? So f prime of minus 2, the derivative of minus 2 would be 0. F prime of 3 is 0. And f prime of 6 is undefined. And it turns out this always happens. The only way a function can switch from increasing to decreasing or decreasing to increasing, the only way you can switch is either by having 0 derivative or by having your derivative be completely undefined. And that's the only way that can happen. So these points on this graph, or these x values for this function, minus 2, 3, and 6, are really special. And for any function, these points where your derivative is 0 or undefined, they're very special. They allow us to change from increasing to decreasing, or vice versa. So we're going to give them a name. We're going to call them critical numbers. Alright, so we'll make this definition. I don't often write down formally a definition, but here's our definition. C is a critical number. C is a critical number for f of x, function f, if C is, and this is kind of important, this is one thing that people forget about critical numbers. If C is first in the domain, it's got to be in the domain of f, so f has to be defined there. C is in the domain of f. I.e. f of C is defined. That's exactly what it means to be in the domain. And that generally just means, just make sure you don't divide by 0 when you plug in C. Okay? So I.e. f of C is defined. And either the derivative at C is 0 or the derivative at C is undefined. Alright, so critical numbers for functions are numbers that the derivative of the function, or sorry, the derivative of the function at the number C is either 0 or undefined. This is precisely what a critical number is, either one of these two things. It's a point where your derivative is 0 or where your derivative is undefined. And a little bit more terminology. People often talk about not just critical numbers, but critical points. So the point C and f of C on the graph y equals f of x is called a critical point. So just a little bit more terminology there. Let me show you exactly the difference. Here, I'll only erase half the board for now. Here's a function. It gets very, very steep right here. But anyway, yeah, let me fix that so it's not too steep. Okay. Here's our function. I have two critical points. Well, I have two critical numbers and critical points. One point here my slope is 0. And here, my slope is 0. Alright, so how about I say this point is x1 and this is x2. I shouldn't say point because they're numbers. But so x1 and x2, these are critical numbers. x1, x2 are critical numbers. They're numbers where my derivative is 0. But the point on the curve, so this point right here, that point would have coordinates x1 and f of x1, that's a critical point. So critical numbers are just the x values. Critical points are the coordinates, the x value and the y value, the actual point on the curve. So again, right up here, this guy would have coordinates x2 and f of x2. That's again also a critical point. And the good news is that's all the theory that we need, right? So let me just try to recall exactly what we've done. We've defined what it means for a function to be increasing. As you increase, you move from left to right. On the graph, your y values get bigger and bigger, right? Decreasing as you move from left to right, your y values get smaller and smaller, less and less if you want. And we've observed that if you want to know algebraically, if I give you a function and I say, when is this function increasing or decreasing, you would take its derivative and you'd tell me whether the derivative is positive or negative, right? And interestingly enough, when the derivative is 0 or undefined, that's the only points where you can switch from positive or negative derivative, from increasing to decreasing. So that's really all that you have to do. You have to answer this question of, okay, here's my derivative. When is it positive? When is it negative? Unfortunately, the algebra behind that, you're solving not an equation, you're solving an inequality. It's the one chapter we didn't really review too much because I'm going to tell you how to do this now. Unfortunately, it's a little bit of work, but I can boil it down to a nice algorithm for you that involves basically just finding the critical points and plugging in some numbers. So here's the test. Test for increasing and decreasing. So, step one. If I want to know when a function is increasing or decreasing, the first thing I always do is I find the critical numbers. Okay, so find all critical numbers. Find all critical numbers for f. Right? How do you do that? Well, you take the derivative and you set it equal to 0. And you say, when's my derivative equal to 0, or when is it undefined? And you know it's undefined just by looking at the form, right? You'd say, when do I divide by 0, or take square roots of negative numbers, stuff along those lines. So find all critical numbers and, just a little bit more, and all points where f is undefined. Again, this almost always comes in the form of dividing by 0. The only other options are square roots of negative numbers or logs of 0 or negative numbers. Right, but pretty much always you're just making sure you don't divide by 0. And what I'm going to do is I'm going to plot them on, I want to say the real number line because that's often what our domain is, but it's really plot them on the domain of the function. Right, so plot them on the domain of the function. So it's usually just i.e. a real number line. I.e. a real number line. And what does that do? I've got this real number line. What I mean by that is just a line going from minus infinity to positive infinity. Maybe from 0 to infinity depending on the actual domain. But I've got this real number line, I plotted some points on there. I'm thinking of those points as breaking up the real number line into different intervals. Okay, so where was I? To divide the line into subintervals. So nothing too bad yet. We just have to find all the critical numbers and also make sure we don't divide by 0 or anything. And we just plot them on the domain. Okay, step 2. Choose any value. Choose any value in each subinterval, any value x from each subinterval, and plug that value into the derivative of the function. Okay, so if f prime of x is positive, or respectively negative, so you take any value from a subinterval, you plug it into the derivative. If you found that that derivative is positive, then that means your derivative is positive on the entire interval. And that means your function is increasing on that entire interval. Okay, so then f prime of x is positive, or respectively negative, on the entire interval. And therefore, increasing on the entire interval, or respectively decreasing if you found it as negative. Increasing or respectively decreasing on the entire interval. So there's actually not a whole lot that goes into this test, right? You really just do two things. You find the critical numbers. That's most of the work. Finding the critical numbers and potentially any points where your function is undefined. And you just subdivide the domain of the function using those critical numbers. And then from each subinterval, you just choose a point. Choose any value, usually nice numbers like 0 or 1 or something. But you choose those numbers and you plug them into the derivative. And you ask, is my derivative positive or negative? If it's positive, it means you're increasing on that interval. If it's negative, you're decreasing on that interval. And you just do this for every single interval. So I'll show you exactly how this works with an example, right? It should make it a lot clearer. Alright, for example, find the intervals on which f of x, so our function is going to be minus x cubed minus 2x squared plus 15x plus 10. Find the intervals on which this function is increasing and decreasing. Decreasing. There we go. Okay, so our function is this cubic polynomial. I'll ask you what the domain is really quickly. And you should identify, okay, so what values of x can't I plug into this? Well, nothing, right? Polynomials are defined everywhere. I never end up dividing by 0 or anything like that. So the domain is from minus infinity to infinity, the whole real number line. But step 1 is I want to find the critical values, or the critical numbers rather. Alright, so I take the derivative. I need to know the derivative. So f prime of x is going to be minus 3x squared minus 2 times 2 minus 4 x to the 1 plus 15. Okay, so critical numbers. We've got two different types. Type A is undefined. When is my derivative undefined? And more often than not, you'll find that you don't have any of these, right? And indeed, in this case, I don't have any because this is a polynomial, and polynomials are always defined. You can plug in any value for x and you get out an output, right? So I actually don't have any of those. But the other type is the zero derivative, so I'm asking when is minus 3x squared minus 4x plus 15, when is that equal to 0? And I should hopefully find some solutions here. So what do I want to do? I'm hoping to factor this. My other option is use a quadratic formula. I don't like to factor with a minus out front. The 3 is pretty bad too, but not the worst thing in the world. But I definitely don't like the minus out front, so I'm just going to multiply both sides by minus 1. Okay. And we'll hope that we can factor this. The 3 throws us for a bit of a loop, but the nice thing about 3 is it's prime. The only way to get 3 as a product is 1 times 3. So if it factors, it has to factor like 3x times x is my leading terms here. And now I need two numbers to multiply together to give minus 15. But when I plug them in here and I distribute, I'm going to end up with 4 x's in the end. So to get minus 15, let's try 3 and 5. Sounds likely. And I think if I do positive 3 here, when I distribute, that'll give me 3x times 3 is 9x's, and then I subtract 5 minus 5x will give me 4x. So this does indeed factor. But if you couldn't see that, if you couldn't factor it, use the quadratic formula, right? You'll still get to the same place. So what does that mean? That means either x is minus 3, there's one critical number, right? X is minus 3, or this one, 3x minus 5 equals 0, right? X plus 3 is 0 gives me x is minus 3, or 3x minus 5 is 0, so 3x is positive 5, x would be 5/3. X is 5/3. So step 1 is almost complete. I've found all the critical numbers. It's not, the derivative is right here, it's not undefined anywhere, but I did find 2 points where my derivative was 0. So what's the rest of step 1? Well, I take a real number line. Well, actually I take the domain of the function, but in this case it is all real numbers, minus infinity to positive infinity. And I plot down on it my critical points. So critical point minus 3 and 5/3. And now that I've got them plotted, I don't actually need them written over here anymore. And last but not least, step 2 said, okay, go to each subinterval. So here I've got 3 intervals, right? Minus infinity to minus 3, 3 to 5/3, and 5/3 to infinity. Go to each interval and choose a number. Choose any old number that you want. So minus 3 to 5/3, let's choose a nice number, 0. If you can choose 0, choose 0. It's really nice. 1 is also pretty good, minus 1 is pretty good. But we'll go with 0. Step 2, now I plug that into my derivative. Okay? So my derivative at 0 is going to be 0 minus 0 plus 15. Is positive 15. What does that mean? That means at 0 I have positive derivative, but it turns out it's a fact that if you have positive derivative at this point in the interval, it's actually positive for every single point in this interval. Right? No matter what you plug in from minus 3 to 5/3, you'll find that it's actually positive. So I'm positive on that entire interval, and that means my function is increasing on that interval, right? Because it's got positive derivative from minus 3 to 5/3. So that's awesome. Now I just have to do that for the rest. 5/3, I want to choose something from 5/3 to infinity. Let's go with a little bit bigger than 5/3, let's go with 2. So plug in 2. My derivative at 2 is minus 3 times 4. So minus 3 times 4 minus 4 times 2 plus 15. If the numbers are hard, you don't really have to know the exact value, you just have to know if it's positive or negative. But here these numbers are pretty simple. I've got minus 12, minus 8, is minus 20 plus 15 is minus 5. The important point is that that's negative. So it's negative at minus 2. That means it's negative on the entire interval. Well, if I have negative derivative on the entire interval, then I have a decreasing function. So we're decreasing from 5/3 to infinity. And we just have to check this interval from minus 3. Choose any value that you want. Here's a little trick. Let me just think about this intuitively. Let's choose a very, very large negative value. Okay? Something like minus 1,000,000. What do I get if I plug in minus 1,000,000? Well, I'd have minus 3 times minus 1,000,000 squared. Minus 1,000,000 squared is a huge positive number, so that's minus 3 times a huge positive number is a very, very huge negative number. And then I subtract off something that's much smaller, and I add something that's much smaller. So if I plug in minus 1,000,000, I get a very, very huge negative number plugged into this. So if it's negative at any point in the interval, it was for minus 1,000,000, then it's negative for the entire interval. And that means it must be decreasing there. So now I've answered the question. Where is this function increasing or decreasing? It's increasing on minus 3 to positive 5/3. Round brackets, right? I'm not going to include the endpoints because at both of these points the derivative is actually 0, so the function is sort of instantaneously flat. It's instantaneously constant. And it's decreasing everywhere else from minus infinity to minus 3 and 5/3 to infinity. So that's precisely how you answer these types of questions, right? You go through these two steps, and that's the whole section. We'll do a few more examples because you should see a few more, but we're going to go through these steps for every single one of these examples, right? Here's a function. Where is it increasing or decreasing? Well, you take the critical numbers. You plot the critical numbers on the domain of the function. That gives you subintervals. You choose points from each subinterval and plug them into the derivative. Very common mistake is to accidentally plug them into the original function. Don't do that, right? I'm plugging them into the derivative because I'm interested in is the derivative positive or negative, because the derivative tells me about the slope, right? Increasing or decreasing. Once you know if it's increasing or decreasing at any point in the interval, then you know the whole interval in actual fact. So we'll do more examples. Here's an example. I won't write down all the words, but it's understood. Here's a function. Where is it increasing or decreasing? So here's our function. F of x is minus 2x over x plus 2. First thing I'll point out is something about the domain of this function. This is not defined for all values of x. Right? There's one value for x that you cannot plug in, and that's x equals minus 2 because it causes division by 0. So the domain would be all real numbers except minus 2. But we'll get to that. So first things first, we take our derivative. Right? We want to differentiate this. This is why we need to be good at differentiating, because if you can't differentiate, if you can't find the derivative of this, then you can't do any of the rest of the stuff. Right? It's the first step to all of these problems. It's a quotient. Right now it's written as a quotient. I'm going to interpret it as a quotient. So to differentiate it, I use the quotient rule. So the derivative is going to be low d high, x plus 2, times the derivative of the top, which is minus 2, minus the top, minus 2x, times the derivative of the bottom, derivative of x plus 2, which is 1, all over the bottom squared. Okay, and we want to eventually ask, where is this equal to 0? Right? When is this derivative equal to 0? So even though in previous sections, if you didn't simplify this, if you just plug that into my math lab like that, that would be fine. Since we want to do more work with this, we want to know when is this equal to 0, we should simplify this. It'll make our life easier. And clearly I want to distribute this out. So I've got minus 2x minus 4 plus 2x over x plus 2 squared. And I want to leave this on the board, so I'm going to write it finally up here. These obviously cancel, right? Minus 2x plus 2x. So our derivative, f prime of x, is minus 4 over x plus 2 squared. Okay, there's our derivative. What now? So now we want the critical numbers. Critical numbers. A, undefined. Is this ever undefined? And the answer is yes. The derivative is undefined when I plug in x equals minus 2. Right? That causes division by 0. That gives us a 0 denominator. So x equals minus 2. But wait. Go back to the definition of critical numbers, and you'll see there's a sort of a one extra part to it that came before the derivative is either 0 or undefined, and that is that critical numbers have to be in the domain of the original function. And x equals minus 2 is not in the domain, so I'm actually going to not consider it. Alright, so b is 0 derivative, so when does minus 4 over x plus 2 squared equals 0, and I'm solving this equation. Two ways you can think about this now. One is I can cross multiply, or just multiply both sides by the denominator here. And if I multiply both sides by x plus 2 squared, I've got minus 4 on the left and 0 on the right. Right? I've got minus 4 equals 0. And that has no solutions. The other way you can think about solving this equation is remember that the only way a rational expression can equal 0 is if the numerator is equal to 0. So immediately, if I'm asking when is a fraction equal to 0, that must mean minus 4 equals 0. And again, that has no solutions. So I have no critical numbers. That's okay though. I'm going to keep going with our technique, our algorithm. And we're going to take the domain of the function. So this is from minus infinity to positive infinity, except not including minus 2. Right, so that's not going to be included. If I had critical numbers, I would plot more on here, and then I would continue subdividing the interval. But I actually still have two intervals here. I've got minus infinity to minus 2 and 2 to infinity. Right, so I actually have two intervals to check. By the way, I'll say that even if it wasn't broken up at all, even if it was just a single interval, minus infinity to infinity, that would be fine. I could just choose one point from the whole interval. But yeah, so now we're on step 2, and we just choose points. So let's choose something from minus 2 to infinity. 0 is a nice number. So we'll plug in 0. Our derivative at 0 is minus 4 over 2 squared. Minus 4 over positive 4 is minus 1. That is less than 0. So we've got negative derivative here, so it must be decreasing. And hopefully you didn't pick up this thought from the last example where it just sort of switched from increasing, decreasing, increasing to decreasing. That doesn't always happen. I don't think that's going to happen here. We'll choose some number to the left of minus 2. Last time I just chose a huge negative number, but let's actually just choose a number here. How about we go minus 3? Oops, I used to do these in red. Go minus 3. My derivative at minus 3 is minus 4 over minus 3 plus 2, that's minus 1 squared. Minus 4 over minus 1 is minus 4, that's also negative. So at minus 3 my derivative is negative, that means my derivative is negative on this entire interval from minus infinity to 2, and that means even here it's still a decreasing function. So we're done. We've done all the hard work. To answer the question, where is this increasing? Well, it's actually increasing nowhere for no values of x. Where is it decreasing? Everywhere it's defined, on its entire domain. By the way, don't include -2 into this, because remember it's neither increasing nor decreasing here. In fact, it's not even defined. So it's decreasing from -infinity up to -2, not including -2, and -2 to infinity. Alright, so it's important that we don't include -2 into this, because the function's not even defined there. It's neither increasing nor decreasing. You might ask how this can be. Well, if I graph this function for you, what does this look like? Here's y equals -2. Here's x equals -2. If you were to graph this function, here's roughly what it would look like. It gets really, really close to -2 in this direction, and then as we go to the right, the function is decreasing, 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 but it's got this vertical asymptote at x equals -2. So it's undefined here, but then it comes back. Then it comes back from positive infinity, and then it decreases, 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 decreases forever. Asymptotically still approaching this y equals -2 point. So this is how it's actually never increasing and always decreasing. It just, it decreases to this asymptote, becomes undefined, and then it continues decreasing forevermore. Okay, how many more examples do I want to do? One more. Okay. Let's say this. The total cost, well, we'll make this a business application. We'll put some words around this. The total cost, C of x, to manufacture a quantity x of a good is given by C of x equals, let's go 2x plus 4 to the 2/5. And the question is, okay, so I've got this cost function. I want to know, when is my cost increasing, when is it decreasing? So where is C of x increasing? Or decreasing? If you want, this is probably a good spot to pause the video, try to do this problem on your own. It proceeds exactly as the other problems, right? We take our function, we want to find all the critical numbers, plot them on a real number line, well on the line that represents the domain of the function at least, and that will give you different subintervals, and you plug in different values for x and ask where is my derivative positive or negative. But if you don't want to pause the video, I'll just proceed with this. So let's see. We want our derivative. So we want c prime of x. What type of function do I have? Well, I've got some function of x plugged into a function that raises everything to the 2/5. Right? So this is special case number 1 of the chain rule. My derivative is going to be 2/5 out front. Inside stays the same, 2x plus 4. Power lowers by 1, so 2/5 minus 1 is minus 3/5. Okay, so there's c prime of x, and my critical numbers A, is this ever undefined? Well, maybe it's not so obvious the way I've written it. How about I rewrite this function? It's let's write this as 2 over 5. So I'll put the 2 on top, the 5 on the bottom, And then the negative power, that means it's in the denominator, right? It's a positive power. So this would be times 2x plus 4 to the 3/5. And written like that, it's more obvious that yes, this is actually undefined somewhere. It's undefined when 2x plus 4 equals 0. Alright, so it's undefined when 2x plus 4, actually 2x plus 4 to the 3/5, when that equals 0. But you can just raise both sides to the 5/3 power. 0 to the 5/3 is still 0. So this really just happens when the base is 0, when 2x plus 4 is equal to 0. And that means x is minus 2. That's actually in the domain of the original function, right? Plug in minus 2 into this original function, you just get 0. 0 to some power is still 0, so it's actually in the domain. So there's one critical number. I have x equals minus 2. How about we keep track of this on the side because we're running out of space. Critical numbers. Lost my chalk here. Critical numbers. Okay. X equals minus 2. And B is, can I ever make this equal 0? 2 over 5, 2x plus 4 to the 3/5. Can you ever equal 0? Well, remember doing this last time, right? The only way a rational expression can equal 0 is if the numerator equals 0. That means 2 has got to equal 0, and that can't happen. So actually we only have one critical number, x equals minus 2. And this looks a whole lot like the subintervals we had in the last example, but minus 2 has arisen in a different way. In the last example we had minus 2 here because it wasn't part of the original domain of the function. Here we have minus 2 because it's a critical number. So slightly different in this case, but we'll go ahead and we'll plug in some values. So we'll plug in 0 again because 0 is always really nice. So C prime of 0 is 2 over 5 times 4 to the 3/5. Now I don't know what this is as a decimal, but I don't need to, right? This is positive on top, and on the bottom I've got 5 times 4 to the 3/5. That's a positive number. Positive over a positive? Well, that's definitely a positive number. Right, so my derivative at 0 is positive. That means my function has to be increasing. What now? Now we'll plug in another number. I'm thinking if we can just think about this as a huge negative number. Doesn't really matter. We'll just plug in minus 3. Okay, so minus 3. The derivative at minus 3 is 2 over 5 times, plugging in minus 3, we've got minus 6 plus 4 is negative 2 to the 3/5. Okay, so how else can I compute this? I can think of this as minus 2 cubed. Minus 2 cubed is minus 8, and then the 5th root of minus 8. I don't know what the 5th root of minus 8 is, but I do know the 5th root, an odd root of a negative number, is an odd number. Or sorry, is a negative number. Odd root of a negative number is a negative number. So the 5th root of minus 8 is definitely negative. What does that mean? I've got a positive over a negative, and that's definitely negative. So at minus 3, whatever my derivative is, it's definitely negative, just by looking at the form of that expression. That means it's decreasing here. So our final answer, where is the cost decreasing? Well, it's decreasing from minus infinity to minus 2, and then increasing from minus 2 to infinity. minus infinity to minus 2. Oops, sorry, it was decreasing there. Let's change the words. Decreasing from minus infinity to minus 2, and increasing from minus 2 to infinity. Let me say one more thing before I wrap up this video. This is a pretty long one. Let me just say one more thing. Typically, you wouldn't consider manufacturing a negative number of goods, right? So, depending on how you interpret this problem, maybe on the way it's stated, you might interpret the domain of this function as just going from 0 to infinity, right? So instead of plotting this whole real number line from minus infinity to positive infinity, you might just say, okay, well, it's really only defined from 0 to infinity, right? I can't manufacture a negative number of goods. That means that that critical number we had out here, minus 2, doesn't matter anymore, right? It's not even in the domain of the function. So you would just have a single interval here, and you would just plug in a point. Maybe you plug in a derivative at 1. If you plug in the derivative at 1, I promise you'll find it's positive, so it's still increasing. But in that case, your answer would just be in a sort of a different world based on how the problem's phrased. You would be increasing from 0 to infinity. No surprise, right? Certainly you would expect, as you manufacture more goods, your cost is increasing. All right, thanks.